All right. You're playing the audio in the background, I think. But anyways, what's up, skeptics? Welcome to another episode of Reason to Doubt, your source for all things skeptical. I'm Jordan, joined again with Jared. How's it going, Jared?
It's going really well. I'm excited for this one.
Yeah, this one's it's been one I've wanted to do for a while. This is kind of a pet peeve of mine when people abuse these poor defenseless laws of thermodynamics. So today we're going to be talking about creationism, usually young earth creationism, and specifically the claim that evolution is impossible because it violates the second law of thermodynamics, because they say evolution requires that things go from simple to complex, and that the second law says everything goes towards disorder or chaos over time. Checkmate, atheists, right?
I've heard that quite a few times.
This is actually one that I heard when I was a creationist, and it was weird because I was like, surely scientists have thought of this. Like, they can't have missed this, right? But then because I didn't know what I was doing.
You just stopped right there.
I just stopped right there. Right? Yeah, exactly. But don't worry, you don't have to stop right there, because I am going to show the math that shows that this is false. So if any creationists try to assert this in the future, you can just direct them to the stream, and that'll cure the whole thing, I'm sure. But also, at the end of it, where I'm also going to be picking a bone with all of the not creationists who talk about the second law in ways that I don't think are accurate or helpful. So we're going to give you the good stuff up front, but then I'm going to pull out a massive soapbox and just yell at everyone. So we're going to hit everybody on this one, as we like to do here.
I'm really excited about this one, actually, because I think this is one of there are many holes in my knowledge, but this is one of the holes in my knowledge, a complete understanding. If somebody were to come to me on the street and say, can you explain the second law of thermodynamics and make me understand it, I would have a hard time conveying that in a way that would be sufficient. So I think somebody like Jordan, who is much more educated on the matter and much more coherent when it comes to explaining it, is going to be really nice. But one thing I was going to ask you, Jordan, when we talking about second law of thermodynamics, what exactly is a law, first of all? Like, how do we know?
Well, a law is rule laid down by a lawgiver, obviously.
Oh, okay.
Yeah.
Therefore, God.
Right. Chat says Jay is a bit louder than the other Jay. That is not helpful. I need you to be more specific as to which one is louder, and then we can fix it. Thanks, chat.
Super helpful.
Okay, so what is a law? A law is an observation of something we see, a way that matter, energy, or whatever behaves, that, so far as we can tell, has no exception. So as a creationist, I was taught it goes hypothesis, and if the hypothesis holds up, then theory, and if the theory does really good, it becomes a law. And that's just not the case, because hypothesis is an idea, right? A theory is like a set of hypotheses or a framework that has resisted falsification, but a law is just an observation. Usually, not just one, obviously. We've seen it over and over and over again. So a law is like one of the things your theories would have to take into account, because it's just an observation of how the world works.
Okay. So when we're speaking scientifically or physically in this matter, in terms of physics, the law is basically the observation that the theory is trying to account for.
Yeah. Well, not necessarily just the laws, because you can have observations that aren't laws,
Sure.
But if your observation contradicts a law, it could be right. It might just be that we've just never seen where the law fails. Like, we thought this was a law, but it's not, and we were wrong.
Gotcha.
That's possible, right? DM says, sorry I'm late, you can start now. We will start all the way over just for you. In order to trigger that, use the slider on the bottom, go to the left, and then we'll have started over. So it's always possible that we could see a new observation that would show that the law wasn't actually a law, right? And so, hypothetically, that could be the case with thermodynamics. But even among laws, which are already pretty solid, we don't call them laws for nothing, right? The laws of thermodynamics are pretty ironclad even among laws, right? Like, to paraphrase physicist Arthur Eddington, if your theory is contradicted by a single observation, sometimes experimentalists mess things up. But if your theory is found to be against the second law of thermodynamics, I can offer you no hope. Like, if your theory contradicts thermodynamics, you're just wrong. So,
Well, cool. It's good to know. So how does this apply then to creationists? Because shouldn't they have to like incorporate this into all their explanations? Or
well, okay. So first of all, explaining the evidence is things that we do, not what creationists do, right? Obviously, if we can't explain the evidence, and therefore they're right. So, but
okay.
where it ties into creationism, that was a joke. They try to explain the evidence poorly. But where it ties into creationism is that they're actually kind of right. Like, what I just said about the laws of thermodynamics being ironclad is right. If it could be shown that evolution violated the second law of thermodynamics, then that would be very compelling evidence that evolution is somehow false. I mean, that's like a big no-no. Okay.
Gotcha.
So it could very well be the death blow to the whole idea.
So when the creationists are doing this, though, I always hear about the second law of thermodynamics, and it seems weird to me that it's the second law. Like, it's just this one thing out there. To me, usually second means there's a first, and sometimes implies that there's a third or fourth.
Those other ones, don't worry about those. They're not important. Yeah. Yeah. There are, in fact, 4 laws: the first, second, third, and 0th law.
Okay.
Because the 4th one they figured out later, but it was like kind of prior, like it kind of fits before the other ones. So they just called it 0. So there are 3 laws. Yes. One you've probably heard of: energy cannot be created or destroyed. Like, so energy will change forms, but the amount of energy in a system will stay the same. So that's the first law, for example. Okay. So there are 3 laws. The other ones aren't relevant to this discussion, but there are more laws. The second one is the only one that matters to this. But if someone brings up the second law and only ever brings up the second law, and you ask about the other laws and they are like, look at you clueless, it's probably a good bet they don't know what you're talking about. But we can talk about the second law. It's expressed verbally a lot of different ways, right? You've probably heard like entropy, or like all systems tend towards disorder, or like the disorder in like a system always goes down. Like, you've heard probably it verbalized a lot of ways, right? But this is a law that's fundamentally math. So there's a lot of different ways to articulate it, and if they're valid, they're all equivalent, right? If the way I'm going to show you is not the only way to look at the second law of thermodynamics, so you can see another conception that's just as valid, that's fine. But this is the second law in math. Okay, the total entropy of the universe, everything, must increase or stay the same in every spontaneous process. So delta means change. S is the symbol for entropy. Why S? I don't know. I didn't come up with it, but that's just the symbol that everyone uses for it. So delta S, the change in entropy in the entire universe, equals the delta S of your system plus the delta S of everything that's not your system, and that has to be greater than or equal to 0. So what's a system? A system could be anything. It's completely arbitrary. You draw the system boundaries wherever you want. It's just whatever's convenient for you. So your system could be your car, or an ice cube tray, or the whole Earth, or the solar system, or the entire universe, or whatever. Wherever is convenient for you to draw your imaginary line, that's your system. Okay? Now, you might have noticed nowhere in this slide or in this law does it say anything about disorder. That word does not appear.
I thought that's maybe what the delta S stood for, but I guess I was wrong.
You were wrong. Don't you ever say that again. So this is going to be on the soapbox, and I'm going to talk about it at the end. But just for now, I'll just say entropy is not disorder. They are not the same thing. Exactly what entropy is complicated. I'm going to try to explain it. But entropy does not equal disorder. If you take nothing else away, please know that. Okay. But if it's not disorder, what is it? Entropy is, again, there's lots of different ways to describe it. Entropy is a measure of how much useful energy there is in a system. Or it's also a measure of like how spread out the thermal energy is in a system. So when energy is used, remember, it can't be created or destroyed, right? It just moves from place to place or changes forms, right? Over time, when you're using it or just naturally, it spreads out and becomes diffused. When there's no longer a differential, you can't use it to do anything. So like if you're going to use like a heat engine or a heat pump or like a turbine or whatever, it requires a change, high on one end, low on the other. That's required. Okay. You can do useful stuff in that flow. Once it's all the same, once the same temperature is everywhere, you can't, the same amount of energy is there, but you can't do anything with it. That's entropy, right? So you can think of it as like just how spread out the energy is. And over time, the thermal energy is going to want to kind of get to equilibrium. Everything will become the same temperature, and then it's done.
Okay.
So if you want to, for right now, if you want to conceptualize it as disorder, you can do that for the next like 20 minutes before I disabuse you of this notion. But that entropy is a thing that goes up, okay? And so we can already see, if I bring up the law again, we can already see that the bottom rung creationists are wrong just from this statement here. Because from this equation, if that delta S system is negative, so your entropy went down, that's okay as long as your delta S surroundings is bigger, because the answer will still be positive, right? So if your entropy of your system went down by 5 and your surroundings went up by 6, that's an increase in entropy in the universe. Totally fine. No problem. So a real world example of this would be in your freezer. We can draw our system boundaries wherever we want. You put some liquid water in an ice cube tray, throw it in your freezer. The liquid water is a higher entropy than ice. Ice is at lower entropy state. So the liquid water becoming ice, that's a reduction in entropy. Okay. And if the creationists were right, that would be impossible. But it's not impossible, clearly, because we do it all the time, right? What's happening is your system, the water, that's gone down in entropy. Its surroundings, specifically that motor in the back of your fridge that's running and producing a bunch of heat, that's increasing in entropy, and is increasing by a lot more than the ice is decreasing. So the universe, as a result of this process, the entropy in the universe has gone up.
Gotcha.
No problem. So I think where this misunderstanding comes in is because they're always talking about, they always want to look at the isolated system, right? So we'll say that the entropy of an isolated system always goes up. And that still works with this equation, because if it's an isolated system, that means that there's no transfer with any of its surroundings. There's no transfer of matter. There's no transfer of energy. So far as your system is concerned, if it's isolated, the rest of the universe doesn't exist. The universe itself is taken to be an isolated system, right? So basically, if your system is isolated, it's a little mini universe, right? Well, if it's a mini universe, then the delta S surroundings goes away. That term is gone. And then you're just left with delta S system greater than or equal to 0. And so in that case, if you're in an isolated system, yes, your system cannot decrease in entropy because there's no surroundings to pay for it. The problem is they hear that, which is valid, but then they forget the isolated part. They just remember that entropy can't go down, and then they run from there. And you may not be aware of this, but there's actually a big source of energy that's coming into the Earth all the time, which shows that it's not an isolated system. You may have seen that fusion reactor that's in the sky about half the day. That's a source of energy. So clearly we're not isolated, right?
Yeah, we just got blasted with some of that energy a week ago. I saw some Aurora Borealis, the Northern Lights.
It's true, yeah.
Yeah.
DN says, let's be honest, most people don't understand thermodynamics. That's correct. You are right. It is a sad truth of the world we live in. But hopefully the 20 people watching the stream will understand it just a little bit better at the end. Okay, so that's the bottom rung, like Joe Blow creationist you might run into there, right? And if they say no system, entropy always goes down or always goes up in every system, well, it's not isolated. That's an answer for that, right? Because a non-isolated system can't have its entropy go down. But that's just your bottom rung.
That system's probably in a larger system where the entropy is
Exactly. Very astute. Every non-isolated system you can imagine is a subset of a larger isolated system because the universe is an isolated system.
Right.
So if you go back far enough, eventually you get to an isolated system. Okay. And the more sophisticated creationists, your AIGs and CMIs and stuff, they obviously have taken this into account, and they say that okay, their objection is not, oh, it's not an isolated system or whatever. They acknowledge that systems can decrease in entropy. But what they say instead is, well, nobody has shown that the decrease in entropy needed for life is paid for anywhere else. And it's such a massive decrease in entropy that you can't just take that and blah, 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 basically. So that's what they say. And they're not correct that nobody's done it, but maybe they haven't seen it, but it's okay. They're going to see it now because I'm going to do it live right before your eyes. So are they right? The short answer is no, they are not right. The long answer is going to take some math, though. So to start with, remember that thermodynamics is all about energy. So we're going to be talking about the transfer of energy from one place to another, and how much entropy is included in that energy, basically. For the math that I'm going to be showing, I'm leaning on Evolution and the Second Law of Thermodynamics by Emery Bunn in 2009. I verified all his math to make sure it was right, and I've rearranged it a little bit. But his paper is where I'm drawing most of this from. Okay, so the idea is from the creationist that life started really simple, became complex to us, and that is a decrease in entropy. That's what they say. Okay. Well, I don't know that that's the case. I actually don't know how you'd even go about measuring that, but we can just assume they're right for the purposes of this, right?
Well, I think it's, if I can interject real quick, I think it's because they think of it as using the word disorder, and they see creation as creating order. So you can't create order if you're at the same time creating disorder, which...
Yeah, I think it stems mostly from the order disorder confusion.
Right.
But we can just say they're right for the purpose of this. That's
Sure.
fine. Icarus says, who doesn't like maths? This guy. I actually am not a huge fan of math, contrary to popular imagination. I like to joke that if you like math and you're good at math, you become like a mathematician. If you don't like math and you're bad at it, you like go do business. If you are good at math but don't like it, you become an engineer. A lot of engineering is figuring out how we don't have to do the math that we're good at. Okay, so here's what happens. The primary source of energy relevant to life on Earth is the sun, right? The sun shines its rays on the Earth. Stuff on Earth absorbs it, plants and various other things. They do stuff with it, metabolize, reproduce, blah, 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 do whatever. And then radiate it back out into space. This you may not realize this, but the Earth gives off just as much energy as the sun puts in. Now, if you think about it, it would have to, right? Because if we were getting in a bunch more energy than we were giving out,
really hot.
It would get really hot really fast. Now, in fact, the Earth is warming, right? But the delta is very small on the grand, like it's still enough to kill us, right? But on the grand scheme of things, it's about equal.
Yeah.
So we're emitting about as much energy as we're getting, but the entropy of that energy is much, much higher. So for every photon we get from the sun, we emit about 20 photons. So same amount of energy, but spread out a lot more, much higher entropy, right? And so you can see that as a result of the system of Earth, the light's coming in low entropy, coming out high entropy. There is a entropy delta there, right? The entropy of the whole Earth has gone up in some way, right? So the question then is that enough? Is it enough entropy to do what we need it to do? We have to have enough entropy to pay for life. Okay, so here's some math of how much we have to work with. What's our budget? Okay, formula there. dSdt, that's the amount of the change in entropy over time, over change in time. That is equal to P, which is the solar radiation at our surface, over the temperature of the sun, minus that same P, because again, they're equal, over the temperature of the Earth. P over T, that's that ratio is tells you what the entropy is. Okay. And the solar radiation of the Earth's surface is the total amount that hits us times the albedo, or 1 minus the albedo, because the albedo is how reflective you are. So not all of it gets absorbed. So you have to take care of the stuff that's not absorbed that gets reflected back out into space. But the 1 minus the albedo is 0.7. You can see the numbers there. We get 1.74 times 10 to the 17th watts. For a total of 1.22 times 10 to the 17th watts is actually absorbed. Temperature of the sun, 5,700 Kelvin. Temperature of the Earth, 288 Kelvin-ish average. So plug all those numbers in. Do those ratios. You can see the math on the screen. If you're listening on a podcast, you'll have to take my word for it, but it's there. Trust me. The answer is 4.0 times 10 to the 14th joules per Kelvin per second. Joules per Kelvin is the unit of entropy. And so that's how much entropy we have per second coming in, basically. Or, well, not coming in. That's the budget we have.
Right.
Now, there's a constant called Boltzmann's constant that comes up a lot in thermodynamics. You don't have to worry about what it is. It's a constant. And I'm going to factor it out because that'll be helpful later. So factoring that out, the target number we have is 3 times 10 to the 37 K. That's that constant per second. That's our entropy budget. All right. So bunch of numbers. The actual numbers don't matter. We just have to be less. As long as life costs less than that, then we're good. Okay. So, does life cost less than that? In fact, right? that's the $1 million question. Is this enough? And it's actually kind of tricky to calculate. Like, it would be hard to figure out exactly how much entropy was going into creating life, right? Because like every different material, like every element is gonna react somewhat differently. Like certain elements have higher like if they absorb energy, that'll be a bigger increase in entropy than other elements. And like life is not a single element, and so like you have to track it between generation. Like it could get very complicated very fast. But the good news is we can just cut all that out and just make grossly generous assumptions to simplify it and go with that. Because if the math works out for our like way overestimate, then we're good. We don't need to do anymore, right? So throwing precision out the window, we can, instead of looking at every life form on Earth, and instead just look at us as like one big pile of biomass, one big pile of carbon that is in some arrangement now, and was in some other arrangement before, right? Now, we have some entropy now, and we had some entropy at the beginning, and that delta for this biomass is what we need. Well, I don't know how much entropy life has now, but I can tell you what it's definitely more than is 0, because that's the minimum entropy. You can't have any less than that, right?
Sure.
0 entropy. So we'll just say, hey, life now, 0 entropy, has none, 0, nada, okay? And then what was in the beginning? Well, I don't know what it was in the beginning, but I can tell you what it's not more than: the maximum. You can take like the maximum of all these molecules. Imagine they're perfectly spread out, thermal equilibrium, everything. There's a maximum entropy in the space for that number of molecules, and the minimum is 0. So the change and this is grossly overestimating, right? This is like you'd have to take every molecule spread around the atmosphere, and each atom is placed specifically in a specific spot by this process. Like this is way, way more entropy than you'll need, but it's simple to calculate. So we're going to go with that. Okay. So let's do some math to see if it works. Here is our equation: the delta S of life. How much entropy change is the result of life? You've got your minimum plus your maximum. Because the minimum is 0, it's just the maximum. And that is this cool formula here: N subscript B, mu over T. N subscript B is the number of molecules for your biomass. Total biomass on Earth, according to Google, is 10 to the 15th kilograms carbon. Now, that's how much carbon is in it. We're carbon-based life, so that's going to be most of it. But let's just multiply that by 100. Like, say the carbon was only 1% of the biomass, just multiply it by 100 to be safe. So that way we definitely capture whatever the number is, right? It's less than that, so we'll just go with it. So that if you do like the cool Avogadro's number and stuff to go from kilograms of carbon to like molecules, 5.02 times 10 to the 42 molecules. And why make math harder, right? We'll just round it up. 10 to the 43. Easy, right? Mu is the typical chemical potential for one of those molecules, just a trait of the molecule, and T is temperature. There's a cool ratio for ideal gas, and because we're dealing with like a cloud of carbon, we can treat it as a gas. And again, that's conservative because gas is high entropy, right? So we're kind of a squishy, mostly solid now, but if we just treat us like gas the whole way, then that'll, again, overestimate it, right? Okay. So we're going to overestimate again. We're going to call ourselves ideal gas, and there's a cool relation. Mu over K, that's the K from earlier. Mu over KT is about -10. It's like 9 or something, but whatever, -10. Good enough, right? Close enough. We'll just round it up. So delta S life equals this thing. If you put those numbers in, 10 to the 44K. Okay? So that's how much entropy we need to go from a completely diffuse biomass spread evenly over the entire surface of the Earth to an perfect crystal with no entropy. Okay. This is so ridiculous. So we have our target now. And so the question is now, okay, that's how much we need. And we have a rate. We know how much we get per second. So how long would it take for the sun to give us that much entropy, to pay for that thing? We have 4 billion years to work with. And, you know, we don't want to take the whole 4 billion because we don't want to be too close. But as long as we're not like right up against the edge, we're probably okay. So if we do the numbers with fingers crossed, the delta T we have is the absolute value of delta life over the rate, right? So we have 10 to the 44K over 3 times 10 to the 37K per second. That's roughly equal to 10 to the 7th seconds, which is less than a year. So in one single year, we get enough entropy in our budget to pay for this ridiculously overestimated biomass entropy thing. And we have 4 billion years to work with. So by a factor of e to the 9, I think we're okay.
Yeah, I think I would think so. Now you kind of lost me there with the seconds. Like, how did you get to the seconds to figure out? So
yeah, so I can go back to, this was our rate, remember? ds dt, ds over dt, that's the change in entropy over every unit time. And so we're seeing how much so much solar radiation is coming to the Earth every second. The units there were watts, and watts are joules per second. Okay. So how much energy per second are we getting? You can do some math to turn that into entropy per second. That's the rate.
Gotcha.
And so then you have your total amount that you need. You divide that by the rate. The units of entropy cancel out. Your constants cancel out. You're left with seconds. There you go.
And this is, like you said, this is a worse, or would it be a worse or best case? This is a...
This is being
generous.
Absurdly generous. This is like probably many orders of magnitude overestimating how much, and I'm not even convinced that the entire premise is right, but it doesn't matter because it's such, the amount of entropy change that the biomass could need is so minuscule compared to the entropy we have to work with. It doesn't matter. Like, we don't need to think about this any further. Entropy doesn't violate the second law no matter how you slice it, even if every single thing they say is correct, even if the whole disordered chaos thing, whatever, it doesn't matter. We have plenty of entropy in our budget, so no worries. Evolution is safe. That has been debunked, done. So, now that we debunked the creationist stuff, but you're all still here, now, since I've been waiting to talk about thermodynamics all this time, you're going to hear about what I want to talk about. And I can't keep you here, but if you want to hear me rant about what bugs me about thermodynamics and how people talk about it, stay tuned, because there's 2 big misconceptions that I really, really don't like. And I think contribute to this kind of poor communication and poor understanding, right? So the first one is the confusion of entropy and disorder, which I touched on earlier. And this isn't the creationists' fault. It's not their fault, because educators for decades, if not centuries, have been using disorder as an analogy for
entropy.
entropy forever. I mean, you probably, if you learned it in school, you probably heard them talk about disorder. They probably like use the example of like, oh, you know how your room gets messier over time. It's like that, right? So like, it's not their fault. But the problem is that it's not a very good analogy, first of all, and it quickly leads you into trouble. So you do have this direct experience of things becoming messy over time. So like, oh, okay, it increased over time. Cool. The problem is that disorder isn't well defined. It's kind of messy. You just kind of know it when you see it, right? Whereas entropy has a very specific definition. So right. So like you have an intuitive sense of what's disordered. You got your bookshelf, all of them lined up neat, and you throw them on the floor. Okay, that's an increase in disorder, whatever that means, right? But okay, that's good enough. But then, like, if you try to actually do things with this definition, it gets really weird really fast. So imagine you had two clouds of gas, okay? Equal number of molecules, same atoms, whatever, okay? One of them is in thermal equilibrium. So one of them is a constant temperature, okay? And it just so happens to be shaped exactly like the Statue of Liberty. Like the cloud is perfectly a one-to-one precise recreation and shape of the Statue of Liberty. Okay? But it's in thermal equilibrium. It's all the same temperature. Then you have another cloud of gas, exact same molecules. It's just in like a messy kind of amorphous blob. But the right half of the blob is hot and the left half of the blob is cold. Well, which one of those two is more disordered? I don't know. I mean, the amorphous blob is kind of a blob, so maybe that's just more disordered, right? I don't know. The other one's shaped like a statue, so maybe that's more ordered. I don't know. It's hard to say. And you can make an argument either way. Well, which one has more entropy? Well, that's easy. That's the statue, because it's in thermal equilibrium. It's not ambiguous at all. The fact that one side of the one blob is hot and it's cold, you have that delta, that is low entropy. It is a straightforward answer with no ambiguity whatsoever. And that's why disorder doesn't work.
Yeah. I think this often is confused because disorder is sometimes used synonymously for chaos, which is different. It's not like you could have the cloud example is a really good example because you could see that if you were to go in there, it's a spread out as far as possible. It can't get no more. It's at zero, like you said. It's completely so.
Okay, but this still doesn't explain to you what entropy is, though. Like I told you about delta temperature, and so you can maybe have a sense, but okay. And I've explained it a little bit earlier. I'm explaining it in more detail now. Like I said, entropy is the useful energy that's left. So I talked about that before. Another way to think about entropy is how many micro configurations you can have without a change in the macro state. So a micro state is like the energy of a specific atom. The macro state is the temperature of the cloud, like the thing you would actually measure, right? And so if you imagine you had a cloud of atoms that are all the same temperature, and you just started switching around atoms, they're just teleporting and moving them around, you wouldn't see any difference in temperature because they're all the same temperature, right? So there's a lot of different configurations those atoms can have, and you would never know the difference, right? There'd be no difference, right? Now, imagine that on the other side, you've got your hot on one side and your cold on the other side. You start flipping atoms. Well, if you flip a hot and cold atom, now the temperature's changed, right?
A little bit, just
a little bit, but it has changed.
Yeah.
Right. Daniel says that definition is only true if the probability distribution of the microstates is uniform. Look, man, I'm trying to break this down to like to crayons. Okay, so don't come at me with your integrals of rho. Okay, I'm just trying to like make it as simple as I can. But the microstate thing is a little confusing. If you just instead can imagine it as how diffuse your energy is, how spread out it is, and energy will want to spread out over time, that's probably a better way. And I think this actually shows you don't need this disorder because you also have an intuitive everyday experience with energy wanting to spread out and get to thermal equilibrium. If my inside of my house is cold because I have the AC on and it's hot outside, and I open the door, the inside is never getting colder, right? Heat never flows from my cold house to the outside. That just doesn't happen. The inside always gets warmer. That's entropy. Right.
Did the outside get colder though?
The outside would get colder because they're going to move towards thermal equilibrium.
Teeny bit.
Well, yes, the outside is a much larger heat sink, right? So like you would probably approximate it's not changing, but it would change a little bit. Okay. So that's entropy is not disorder. Disorder is a fuzzy thing. It doesn't have a good definition. It'll lead you down bad paths. Just think of entropy as the spread outedness of your energy, of your thermal energy, and you'll be okay. That'll be good enough to get through whatever it is you need to get through. Okay. So that's that one. That's more broadly applicable. The next one is people say that the second law of thermodynamics only applies to isolated systems. We talked about this before. AIG cites it as a typical evolutionist answer. And they're not unfounded in saying this, because when I see this in the wild, even people I know who should know better, they'll get this objection. They'll say, oh, not an isolated system. Second law doesn't apply. Move on. The second law applies to all systems. All systems. I don't care if your system's open. I don't care if it's closed. I don't care if it's isolated. I don't care if it's halfway. I don't care. It applies all the time forever. If you are in this universe, by God, the second law applies. Okay?
All right. So first we should define what an isolated system is, though, so we can say why this
got
doesn't
three
work.
states for your system, basically. Okay? We remember system boundaries are arbitrary. You can draw them however you want. Okay? So you draw your boundary. If your system is open, it means that mass and energy can freely flow through that system boundary, nothing stopping it. So like I could say that this little spot of air here, that's my system. Well, that's clearly an open system because that's moving in and out and all sorts of stuff, right? That's an open system. A closed system is like that one. Mass can't go in and out. So if like I had a box, for example, like a metal box that's sealed. Okay, it's a closed system, but it's not an isolated system because heat, energy can still transfer in and out, right? So it's hot on the inside, it can still radiate through, okay? So an isolated system is a system where energy can't transfer either. Now, this doesn't exist really. I mean, the universe is said to be an isolated system, right?
But we outside don't know.
Of the, I mean, yeah, we take it to be an isolated system, whatever. But like no actual system in real life is truly isolated, but you can get ones that are like really well insulated. They're pretty close, you know, you can call it isolated, right? That's what an isolated system is. So far as an isolated system is concerned, the rest of the universe does not exist. Okay. And so that's the second law applies to that isolated system in a very simple way. There are no surroundings. So the entropy of that system, which so far as the system is concerned is the whole universe, must go up or stay the same.
Gotcha.
Okay. Now take that open system. The second law still applies. And it applies because the only thing that changed is now you have to track what's going on outside your system too. You have to measure what's going past those boundaries, right? That's the second law in action. If we go back to the second law in math here, if you're an isolated system, that delta S surroundings, that's gone, simplified. But the second law exists in a non-simplified form right here, right? So all that means is that if you're not dealing with an isolated system, you have to track what's going on outside. You have to track what the flow is. You have to make sure your operation, if it lowers your system entropy here, it's paid for elsewhere, but it still applies. It applies to every system forever and ever. Amen. Okay? And if you basically imagine like you said before, your system, whatever you drew, is a subset of a larger system, the universe, and that system's entropy has to go up.
All right. You would think from a practical standpoint, I mean, you said it before, we draw an imaginary or arbitrary boundaries around things, and that may be a closed system, that may be an open system, but that just complicates things, and because you said you have to track it. So whereas an isolated system, a true isolated system, if I had an isolated system this small, that would be easier to calculate the entropy over the whole system. But because we're working in thing as big as the universe, it makes it kind of difficult.
Well, it would be very unwieldy to have to actually measure the entire universe
Right.
entropy every time you did something, right? So that's why we use smaller subsets, but you can like approximate. So like for the purposes of our like Earth system, I could approximate the solar system as an isolated system. Is it isolated? No, but it's probably close enough. Like,
Sure.
if we're worried about like where's the main source of energy coming from, the sun, we're not getting that much energy from anywhere that's not the sun. So like, and energy is flowing out, but like, okay, we can just pretend like the rest of the universe doesn't exist. It goes off into space, but it's still like part of our system. You can just kind of pretend it's isolated, and you'll get an answer that's close enough. And in engineering, close enough is good enough, baby. Like I don't care if it's wrong. I just need it to be close enough. Like Creationist said, "Oh, it's hard to measure the universe now. What kind of engineer are you? Not a very good one." Au contraire, engineering is the art of approximation. It's the art of knowing what you don't have to do. If you can take a shortcut that gets you close enough, in thermal systems design, Dr. Chen was talking about how like Newton, he wanted to know the density of the Earth, so like he went out in his backyard and like scooped some dirt in there, and like, oh, there's water, so he poured some water in there and did some leaves and stuff and measured the density. And it was like a number. I forget the density of Earth now. Hold on. Density of Earth, 5.5 grams per centimeter cubed, right? He was like, so he measured it and it was like 6. And then we come out with all these like lasers and like extra technology and we get 5.51. He's like, that 6 was close enough. Like,
yeah. So I guess the one thing to go back to this idea of the isolated system, though, the idea you're trying to hit home here is that the second law applies to any system and all systems.
Right. It's just what you have to do with it changes. How hard it is to track changes, right? But it always applies. Your entropy of the universe will always go up, and that has to be true. So now, so Daniel Linford here is try to keep things simple. He says a system at thermodynamic equilibrium will under fluctuations where entropy fluctuates to a lower value. If you wait long enough, you'll have fluctuations of any sign you want. Undergo, right? And this is true. So all this time I've been talking about the second law as a hard and fast rule because it's a law, right? And it's never violated. Well, it's actually kind of stochastic in nature, it's statistical. So you can violate it for a short period of time. It just won't last very long because there's a lot more ways to be high entropy than low entropy. And so you're just like, if you were just to pick a probability, like a state out of the air, you're probably going to get one that's higher than lower. So, right. So like if you zoomed in really, really close to your entropy, instead of being a straight line up, it would like wiggle a little bit, right? You'll get fluctuations. And what he's pointing at is if you're at thermal equilibrium where entropy should be the same because it's maxed out. Well, it won't actually be maxed out. It'll be fluctuating a tiny, tiny bit, right? How big those fluctuations are is a probability function, and technically any fluctuation is possible. They're just vanishingly more improbable the bigger they get. But if you waited for sufficient time, you could get a fluctuation as big as you wanted. So all that's true. None of it's at all relevant to what creationists are talking about, which is why I didn't mention it. So I guess I'll caveat here at the end. This is all models are lies. Some are useful. This is just like how you got taught something in elementary school. Like they said, hey, speed. Like this is time. It's the same for everybody everywhere. And they get to high school and they're like, yeah, remember that time thing about how it's the same for everybody? Yeah, it turns out that's a complete lie. We just lied to you. Well,
it was useful for what you needed to do back then.
Yeah, it was useful then, but it's wrong now. Okay.
Right.
What I'm telling you is useful now. There are exceptions. There's caveats if you like. Yeah. But for what we're talking about, it's there. Icarus asks, if the Earth's climate is at equilibrium, does it get hotter? Is the entropy constant or does it go up or down? So there's a difference between the Earth's climate being at equilibrium, like the average temperature being at equilibrium, and it being a system in thermal equilibrium. It's clearly not a system in thermal equilibrium because space is really cold and Earth is not that cold, right? So you can already see that we're not at thermal equilibrium with our surroundings because if we were, we'd all be dead, right? So Earth is not like that. Earth is not a system in thermal equilibrium. Earth was in thermal equilibrium. Like, we imagine we were a rogue planet. We get kicked out of our solar system or something, go into deep space and freeze. So we become in thermal equilibrium with space around us. Then the entropy would stay constant unless something acted on it to change it. Because there'd be no... once you're thermal equilibrium, it just kind of... I mean, like Daniel said, it doesn't... not technically constant, but it's constant for the purposes of what we're talking about. Yeah. So, Road Squatch asks, I'm not sure if the garden was on Earth first, but the garden was older than Adam and Eve. There was no Garden of Eden. I'm sorry to break it to you, Road Squatch. But the garden would have to come first. So Icarus clarifies, I meant that the energy from the sun is equal to the heat radiation of the Earth. That is true. But remember, the energy is the same. The entropy is not. So we get whatever the number I said was some... well, I'm just going to put a number. It's not the number. I forget what it was, but it doesn't matter. It's 10. We get 10 Earth sun units of energy, whatever, right? We bring in 10. We kick out 10. We kick out the same amount of entropy. But for every photon we get from the sun, we send out 20 more. Same amount of energy, way, way, way more entropy. If we were in thermal equilibrium, there wouldn't be that delta. That change in entropy wouldn't be happening, right? So the fact that the sun is way hotter than us, that means we are not... the whole system is not in equilibrium. We are working towards equilibrium all the time. The sun is doing its best to heat us up, and we're doing our best to heat space up. But yeah. So don't get confused, like the temperature on Earth being mostly constant-ish, like compared to the sun. That is not the same as being in thermal equilibrium. I can see why that might get confusing, but the Earth is not in thermal equilibrium. Okay.
So there was a comment earlier about he talked about dating this universe, but even if we were to assume other universes in the system, again, that's an arbitrary line, and we just say, boom, the entropy has to include... second law has to include all those universes at that point. You just keep going further.
Yeah. So the entropy of the universe of... so I said universe to avoid the isolated system confusion.
Sure.
But the entropy of any isolated system, which includes the universe, must go up or stay the same as the result of any spontaneous process. So you can look at it from the whole universe. That's fine. You can look at a subset of the universe, and then you just kind of have to track what's going on. You can approximate a subset as its own mini universe. If that is valid, it may be valid for your purposes. But yeah, hopefully that answers that question. So let's sum up real quick. The creationists say that the second law of thermodynamics precludes evolution because life requires a reduction in entropy, and you can't reduce an entropy. That's wrong, because you can reduce an entropy as long as that reduction is paid for somewhere else as part of the same process. Okay, you can, just like ice in your water in your freezer becomes ice. That's a reduction in entropy, and the physics doesn't break down. The universe doesn't explode because it's paid for elsewhere. So the only question is the low entropy energy we get from the sun, and then the high entropy energy we emit. There's a delta there. There's a change. Is that change enough to pay for whatever reduction of entropy that life has, if life has a reduction? And the answer is yes, in far less than a single year, and we have 4 billion years to work with. So I don't know if you were worried about evolution being disproved on this live stream, but
I was kind of hoping it would be. That'd be pretty cool.
That, yeah, Nobel Prizes. Boom,
Nobel
right
Prizes.
Yeah. Well, that's everything we had to talk about. And I don't see any more questions in the chat. So thanks everyone for coming. If you would be so kind, if you thought this was useful, drop a like and comment letting us know what you thought. If you have other creationist arguments that you run into out in the wild that you'd like us to address, be sure to tell us. I was a young Earth creationist. I was going to say it was a young Earth creationism. I was a young Earth creationist back in the day. This is surprising for some people to hear, since I am very much not one now. But this I like to view this. That's part of the reason I do this channel, is to try to talk to people who are in, or reach people who are in the same situation I was in, where I was very curious, but I just didn't have the tools, the questions to ask. And so hopefully this helps you, or you can help one of them ask better questions.
So what happened was you were a young Earth creationist. The second law of thermodynamics took you from a state of order to disorder, and now you're an atheist.
Yeah. Actually, it's funny because the second law, even though the second law of thermodynamics only applies to thermodynamics, but the kind of conception of it can apply to other things, such as genes. So what I want everyone to do after you're done here, right? Leave your comment down below, do all that stuff. But if you would all do me a huge favor, I want you to go to Creationists channel and tell him that you learned on Reason to Doubt that entropy also applies to genes, and so you want him to tell you about genetic entropy and how it's definitely a fact. If you do that for me, I'd greatly appreciate it. Okay, what do we have coming up? I actually have we have another Shroud Turin thing coming up at some point in the near future. We have to talk about
Neutrons.
radiation, neutrons, and Bob Rucker's hypothesis. So if you want to hear that, subscribe so you'll see, and hit the little bell. But until next time, remember, you've always got reason to doubt.
Peace out.